Hello everyone, my name is Abiy Malaku and I'm currently a postdoctoral researcher at UC Berkeley. This is a tutorial session for Neheri SimCenter's WeUQ tool, and in this tutorial I'll try to demonstrate the capability of the tool for characterizing atmospheric boundary layer flows using large eddy simulation, with the primary objective of utilizing this simulation results to inform our wind load analysis later on any particular structure. Just to give some background about the tool, the term WeUQ is an acronym that stands for Wind Engineering with Uncertainty Quantification, and it is one of the open source tools developed by Neheri SimCenter for predicting the response of a structure subjected to wind loading. The workflows implemented in WeUQ have special capabilities for modeling and propagating uncertainties present both in wind and structural parameters. You can run these workflows right on your local machine as well as on high-performance computing platforms provided by DesignSafe. You can find more resources about the tool from our official webpage, where you can download the software for free. You can check some of the application examples that we have in the documentation page. If you have any specific question about the tool or particular implementation of certain algorithm in the tool, you can let us know that in our user forum. And for running some of the high-fidelity simulations in this tutorial, you need access to high-performance computing resources. And you can get one for free from DesignSafe by just creating an account. You can follow the link provided here at the bottom. Here is a brief outline of what we're going to cover in this tutorial. First, I will give a short introduction of the CFD-based workflow implemented in WeUQ. Then I will describe the numerical examples that we're going to use in this tutorial. Then I will open the software and walk you through the CFD workflow, demonstrating how we can define the CFD model and run our simulation on HPC resources provided by DesignSafe. Then finally, I will demonstrate how you can retrieve the simulation data back to your local machine and post-process the results. Before directly diving into the tutorial, in the next few slides, I will describe the CFD-based workflow implemented in WeUQ. Here is a schematic representation of this workflow that mimics the standard procedure typically used in wind engineering practice. It tries to model all those important factors determining wind load on any particular structure, such as the wind climate, which is incorporated by providing information related to mean wind speed and directionality. Then we have the terrain effect, which is accounted by providing appropriate boundary condition in our CFD model. And we have the aerodynamic effects, which are represented by running high-fidelity CFD simulation and extracting the wind loads from those simulation. And finally, we have the dynamic effect, which is incorporated by running a time domain analysis of the structure using the loading provided from the CFD models. And finally, we evaluate the engineering demand parameters. All right, now let's look a little bit closer into the process of modeling wind effects on buildings using computational fluid dynamics. Suppose that you have a tall building, very simple geometry, as you see here, and you want to evaluate wind load on this building using CFD. So the first step to create a CFD model is to define your computational domain, as you see here, that encompasses your building, and specify appropriate boundary conditions on the outer surface of your domain. So from all those boundary conditions, the most important boundary condition is the one that we specify at the inlet of our domain, and this boundary condition has to reproduce atmospheric boundary layer turbulence. And for that, it has to be a transient boundary condition at the inlet. And when we run basically the simulation, the the flow dynamics evolves as the wind goes downstream. And what we are interested usually is not the wind profile that we are specifying at the inlet of our domain, but the profile of the abial flow right at the building location. So if there is a mismatch between those two quantities, we need to do a little bit of calibration such that we reproduce the appropriate boundary condition right at the building location. For this, the typical procedure used in computational wind engineering literature is to create an empty domain simulation without the effect of the building and measure the wind profiles right at the building location and compare those with the target values. If we are matching the target values accurately, then we are okay to run the wind load analysis that you see here. But if we are not matching the wind profiles accurately, we need to run additional simulations, changing the inflow boundary condition such that we match the target wind profiles right at the building location. Once this iterative process is completed, then we transfer the boundary condition and all the setup that we have for the empty domain simulation into the main simulation and kind of run the final wind load analysis. And in this tutorial, I will try to demonstrate this process, the one on the left side of the slide, using numerical example that is based on experimental measurement. Before we get into the details of the numerical example, in this slide, I will try to describe the step-by-step procedures that we are going to follow for creating a CFD model in WeUQ. So this workflow essentially is quite a streamlined workflow for computational wind load evaluation. So that means you don't need to put a lot of information to generate the CFD model. If you just provide some basic wind engineering input parameters, then the CFD model will be automatically generated for you. So the first step in this workflow is to create your geometry. Since now we are running empty domain simulation for calibrating the atmospheric boundary layer flow, we need basically here to prescribe the extent of our computational domain. Once we did that, then the next step will be to generate computational grid. You can create a mesh with different level of refinement in your domain in the workflow and run the mesh right on your local machine and visualize it. Once we make sure that the meshing is completed, the next step will be to define the boundary conditions, which include the inflow or surface roughness boundary conditions. After completing this step, then we need to specify numerical settings, such as the type of solver that we're going to use, the time step, and the number of iteration per time step for the type of solver that we already selected. Once we did that, then the next step will be to specify all those quantities that we want to be monitored from the simulation, which could be the wind profiles or local wind fluctuations on the building facade or integrated loads on the overall structure. So after we specify what we want to monitor from the simulation, the next step is just to run the simulation on the remote server and then retrieve the simulation data back. Once we get the simulation data, either you can look into the wind profile and compare it with the target profile, or you can also dive a little bit deeper and check the flow field using third-party software packages such as ParaView. This tutorial is distributed with all the files that you need for setting up the model in WeUQ. Here are the list of files that you need to have. The first is a case directory that contains all the OpenFOAM setups, which includes the mesh as well as the dictionary files. And then we have a JSON file named CS input, and this file contains all the inputs that you need for WeUQ. Basically, you can import this JSON file into the workflow and automatically populate all the fields that are needed for creating the model. And lastly, we have a CSV file named wind profiles, and this file holds the boundary conditions that we're going to use at the inlet. And we're going to feed this boundary condition to the turbulent inflow generation tool that we have and prescribe atmospheric boundary layer turbulence at the inlet. So make sure that you have all these files in your directory before trying to set up the model in WeUQ. Here are more details about the CFD models that we're going to create in this tutorial. It is based on experimental measurement taken at Tokyo Polytechnic University. You can find more details about this experimental measurement from the link provided here at the bottom. So here what we are trying to do is to recreate this experimental measurement in our CFD workflow. So we are planning to use pretty much the same conditions used in the experimental measurement so that we can compare our results with whatever measurement data we have from the wind tunnel test. So now let's go directly to WeUQ and see how we can recreate this CFD model. So the first step is just launch WeUQ, and from the tools, select MPT domain simulation tool that you see here. Then the next step will be, I hope you have already got all the files that come with this tutorial. So in this step, we're gonna actually go to that directory and load the simulation inputs. So for that, you click browse and select the directory that contains the input data needed for this tutorial. So you go to WeUQ here and select that simulation files directory, and it will automatically populate all the data needed for your simulation with the mesh information. So here in the workflow, the first step is to define your geometry. So the first input that you see here is geometric scale. So we are trying to reproduce existing experimental measurement. We are not running everything in full scale. So we need to put the geometric scale of our simulation. So in the experiment, they used a 1 to 400 scale. So we're gonna use the same scale as the experimental measurement. Then the next step will be to define the extent of your computational domain. Here you specify the domain lengths, domain widths, and height. And the other important information here is the phase length. So the phase length represents the distance between your inlet and your target location where you intend to measure the wind profiles, or the place where you wanna put the building for actual wind load evaluation. So that's what the phase length is. So once you specify this information, the next step will be to create the mesh. So you can create the mesh into steps. The first step is to create a background mesh. The background mesh usually is pretty much a regular grid. So you're gonna specify the number of grid points in X, Y, and Z direction. So it is usually recommended to have the same, almost equivalent grid size in the three principal directions. So make sure you don't have really distorted mesh. So once you create the background mesh, you can run this part of the mesh by just clicking the button here, run background mesh. This will automatically create a grid based on the information that you provided. As you can see here, you can see the mesh in different ways here. You can either look at the whole mesh, or you can just see a breakout view of the mesh without some of the exterior face of the computational domain. Then the next step is to define your refinements. So here you can add refinements by putting boxes in your domain and specifying how refined you want the mesh to be in that box. So each box should have the starting and ending points based on the coordinate system originally used in the CFD model. So here we specified 3 boxes with each having further refinement level as you go from the base mesh. So once you create all these boxes as provided here, the next step will be basically to run your final mesh and see how the mesh look like. So here in the run mesh part, you have run final mesh. So if you just click that, it's gonna run the mesh with both regional refinement and as well as a background mesh again. All right, now the mesh is already completed. So you can see that all those boxes were created, and we had multiple refinements in each region. So you can add more boxes if you want, and create more denser mesh at the location where you think you need to have more refinement. So once you complete the mesh, the next step would be basically to define your boundary conditions. In here, we have the first option where you put the velocity scale, reference wind speed, and reference height, as well as aerodynamic roughness for the exposure condition. So this input file is automatically loaded, but I will explain a little bit further what these parameters actually mean. So the first one is the velocity scale. So we are reproducing the experiment at a reduced scale, at a smaller scale. So we are not running everything in full scale. So because we have already specified geometric scale, we need to put also velocity scale so that we can scale our measurements or wind profiles or results later into full scale easily. So you provide that information in here. Then the next one is a reference wind speed. The reference wind speed is defined at some reference location. In this case, we define the reference wind speed at 0.3 meter, and it is 10.6 meter per second. Then the other parameters that we have here is the roughness length. This is specified in full scale in here. It represents the surrounding exposure condition. So this is aerodynamic roughness height, which is almost equivalent to suburb or urban exposure type. Then we have here the time scale, air density, kinematic viscosity, and Reynolds number. So the time scale is automatically calculated based on the velocity scale and the length scale we provided earlier. And the Reynolds number is automatically calculated based on wind speed at the reference location and the reference dimension that you provided here. So once you put all those information, the next step is to feed the input needed for the inflow generator. So I have already mentioned this in the data that was distributed with this tutorial. We have a CSV file containing information about the boundary conditions. So here at the inlet of your domain, you need to select tinf option and import that boundary condition. So if you go to this part of the workflow where you see inflow generation and select digital filtering method and select table to import the inflow data, and click the CSV button that you see here and locate to the place where you saved your tutorial data. In our case, I'm gonna go same location I loaded my simulation data, and go to VUQ and select wind profiles. So this will automatically populate what is needed for the inflow generator. So you can look into the wind profiles, the data. So this is basically tabulated data containing height, the height information, like where the profile, how the profile is specified. Like here, we are specifying the profile along the vertical axis. So it specifies mean wind speed, Reynolds shear stresses, and Reynolds normal stresses, as well as length scales at different elevation. And for the rest of the elevation, it's going to be interpolated linearly. After specifying the boundary conditions, the next step will be to set up the numerical options. So here first we need to pick the turbulence model that we're going to use. In this case, we are running transient simulation. So we need to select LS option from the options that we have in here. Then for the LS, we have to also select subgrid scale model that will be used. So in this case, we are using the dynamic subgrid scale model, which will calculate the subgrid scale coefficients dynamically as the simulation progresses. And once we select that, then the next will be to specify the type of solver. So we're gonna use for the simulation Pimple solver, which is a relatively stable type of solver provided by OpenFOAM. And we need to use this default settings specified for the number of inner and outer correction loops. And once we did that, then the next option we need to be careful is duration of the simulation. So in the experimental measurement, the simulation was run for 32 seconds almost. But in here, we are running it for 34 seconds. Basically, we want to cut the first 2-second duration so that we achieve quasi-steady fluctuations in our domain. So we're gonna take away the first transient part of the simulation. So essentially, we're gonna use the same duration as the experimental measurement after we take that 2-second duration. Then we need to select also the time step. In this case, basically you can calculate the time step by just pressing this option. So this will automatically calculate the time step that you need based on the maximum current number that you specified in here. So it was about 0.007, but we want to round it a little bit to something reasonable. That means 1 times 10 raised to minus 3 seconds. And because the type of solver that we used in this case is a Pimple solver, which is relatively stable for even higher current numbers, using this time step will be justified. So after that, we need to select that we're going to run the simulation in parallel and specify the number of processors that we're going to use. So I recommend using the default values that come with the tutorial. Then after you finish that, the next step will be to record your wind profiles. So for this, we need to measure, we need to specify what we want to measure from the simulation. So here we have at least 3 profiles. The first profile is a profile that we're gonna measure right at the inlet of the domain. So you will specify this line probes by specifying the start and end coordinate of the line. So this is a vertical profile that we measure at the inlet. Then we have also another profile which is located at the location of incidence. So you specify the start and end coordinate of this profile as well, and also you need to specify the number of points in those line profile measurements. So for each of them we used the same number of points, which is like 50 points along the line, and you have to also specify at the same time what field you want to monitor. In this case we're going to monitor velocity, so you have to specify velocity. And for the last profile, this profile will be running in X direction, that is in a streamwise direction. You can always change the start and end coordinate, so it's going to run from the inlet up to the outlet of the domain, and it has 50 points, and in this case we're going to measure pressure, so that we see how the pressure profile decays as the flow goes downstream. In addition to the line probes, you can also specify plane and monitor the whole flow field on that plane. So in this case we're gonna have two planes. So the way to define a plane for monitoring the flow characteristics is first to specify the normal axis. In this case, if we say for example plane 1, the normal axis should be the y-axis, and we specify the base point. So if we specify a point on the plane and the axis that is normal to the plane, then we have completely defined that plane. Then you have to also specify the start and end of the duration for monitoring this data, because we cannot save everything from the simulation. So we have to just only save very limited amount of data so that our space is not crowded. So in this case, we're gonna measure the VTK planes from the first second up to the third second, almost for 2-second duration. And we need to specify also what field we want to monitor. We want to monitor just the velocity or the pressure or whatever field we are interested. So we have basically two options. So we will you need to select the velocity option in here for both planes. So once you complete this, the next step will be to submit this simulation. So before running our simulation, we need to log in into DesignSafe first. So you click login in here, provide your credentials with username and password, and hit login again. So this will log in into DesignSafe system. So once you did that, the next step would be just to submit this simulation. So from the bottom of this window, you can see that Run at DesignSafe option. So you click that, and then provide the name and the number of nodes as well as number of processors, and submit the simulation. So here for the job name, you can use whatever is descriptive for you. I'll use just simple empty domain version to here, and then let me change this one, 3, and then specify the number of nodes. In this case, we're going to run this whole simulation on one node, and the server architecture that we are using in this case has almost 56 nodes, cores per a node, and we're going to use all of them. So you need to put number of processors per node here as 56. Make sure that this number matches with whatever number of processors that you specified under numerical setup tab. And then the next thing that you need to be cautious is maximum runtime. So in this case, I have already run the simulation previously, and I know how long it's going to take to finish the simulation. So basically, this process is a trial and error, but for now, we're going to use whatever durations that I have used before, which is like approximately 4-point-something hours. It needs that much time for the simulation to complete on the server using 56 cores. So which means like we need at least 5 hours. So I'm gonna use 5 times 60, which is equal to 300 minutes. So you're going to specify that here, and then also the allocation type that you're going to use. So for this one, we will be using design safe sim center option, and then hit submit. So this will take a little bit of time until it actually compresses everything and sends into the server. So once that is done, next you can monitor how the simulation is going. So you can do that by just clicking get from design safe option in here. If you click this, it will just give you all the list of jobs you already submitted to design safe and the progress under the status column that you see here. So if I go to the job that I just submitted, which is MPT domain version 3, you can say refresh job, and now it has just updated, and it is kind of actually staging the job and sending the data into the server. So once your simulation is completed, this option will be finished, as you see in here for the other simulations. So this basically tells you can basically download the simulation and visualize the results. That's how you submit a simulation. Now, I have already done the simulation previously, so I will just load that simulation data and show you how you can post-process the results. So if I go here, this is the simulation that I submitted before, and say retrieve data. So this will automatically retrieve previously submitted data and populate the result tab of your workflow. So it's going to take a little bit of time. All right, it just finished loading the results. So here we have already specified what we want to monitor from our simulation, which means we are monitoring 3 profiles, 2 wind profiles and another pressure profile. So here it will show you the wind profile. So if you select profile 1, which is measured right at the inlet, and say plot profile, it will plot this profile against to the target profiles used at the inlet. So as you can see here, we have the mean velocity, turbulence intensity in the 3 principal direction, IU, IV, and IW, and as well as the length scale and shear stress profiles will be shown here together with the target. So you can also do the same thing for the velocity spectra. So for this one, you have to pick 2 things. First, you have to select the profile from which you want to plot the velocity spectra, and also specify the height. So by default, we calculate the velocity spectra at 4 heights. The first one is just 0.25 times the reference height, which was specified under your boundary condition in here, under wind characteristics subgroup. So if you select, say for example, 1 ref height, it's gonna plot the velocity spectra at this particular height for profile 1. So if you just click this one, it will show you the velocity spectra for the 3 components, for U, V, and W components, together with the target von Karman spectra, which is shown in here with a black line. So this is a reduced frequency, and this is reduced spectra, and it shows how good or how far we are from the target von Karman spectrum. And you can also do the same kind of comparison for pressure fluctuation. So the third profile that we are measuring is basically pressure. So if you say plot pressure, it's going to show you how the pressure fluctuations decay as you go downstream. So this is basically very important because we're going to put our building right at location where we don't have this the effect of this artificial pressure fluctuations. So for example, if we place the building say for example right at the inlet, we're going to experience a lot of pressure noise fluctuation coming from the turbulent inflow data, and that might contaminate our simulation results downstream. So it is always recommended to put our building relatively far from the inlet so that we don't have the influence of the boundary condition. So in this case, say for example, if we are placing the building around 2 meters away from the inlet, then most of that artificial turbulence fluctuation has already died. So it is safe to put the building right here. So this is how you analyze your simulation results for the MPT domain simulation. Now let's look into the flow field data. When you download your simulation results from the server, essentially it will save it into the default directory, which is located in your documents folder. So this is the path where the results are saved. So let's copy this one, and we will look into this directory and see how we can load this simulation data into a third-party software called ParaView and look into the flow field. So let's copy this one here, close the window and open ParaView. So here you can locate this directory by just opening a path. So you can just paste the path here and look into this directory. This is a directory which contains the OpenFOAM folder with all the simulation data saved. So if you just click the VisFOAM file, it will automatically load the simulation data into ParaView. And you can see here the pressure field. You can also select U, which is a velocity field, and you can visualize the distribution of the velocity at some particular time step like this. So this was recorded at the last time step, which is 34 seconds. We cannot save every time step for the entire computational domain. That's the reason why we need to save that VTK file on particular plane and kind of record for some limited amount of time, because we don't have space to save everything at each time step. So now I will also show you how you can download those VTK files and see the evolution of the flow downstream from the inlet. So to do that, you can also go to the same directory, and in the post-processing folder, you can see plane 1 and plane 2 options. You can select, say for example, plane 1 here and click this one, this PTK files here, and you can visualize that in here, because here we are showing both the VTK and as well as the whole computational domain. If you just turn off the computational domain, it will show the VTK plane that we recorded. So this is basically just a simple rendering. If you want to see the velocity, you can select U in here, and it will show you the velocity field in the whole plane. Let's create just a simple video and see how the flow field develops downstream. So if you just in the animation panel that you see here, if you just say play here, you can create a simple flow visualization of the turbulent inflow that we specified at the inlet. So you can do the same thing for the other plane, and this concludes this tutorial, and thank you for attending.